Now these are the two things. So partition function now is 1 plus Fij, but is a product. So now I can do the product. The first product, all of them are 1. So I write 1 plus C, this is a binary. So 1 plus F12, 1 plus F13, 1 plus F14 dot dot dot, then multiplying 1 plus F23 plus 1 plus F24 dot dot dot, that 1 plus F34, 1 plus F45 dot dot dot, like that. Clear, no? It is not in chemistry, you don't come across this kind of somewhat intellectually demanding things where you are doing formalism. But this is one of the simplest at this level. Okay. If I do that, then every product has a 1 in front of it. So one of them will become 1, right? Then all of them, so I multiply, then next one will be binary term. Okay, let us do the simple one to see that it is the way it is working. So let us see, I have 3 particles. Dr3, okay. Then I have is that okay? Now if I do that, first term is 1, next term is F12 plus F13 plus F23, okay. Then next term is binary F12 F13 plus F12 F23 plus F13 F23, then I have one term F12 F23 F13. So I have this term, then bunch of 1 particle term, then there are 3 particle terms, but the 3 particle terms of 2 kinds. One of them is okay. So now remember, this is an integral. There are too many things to say, so I will go back and forth. So this is a kind of the 0th particle term. This is the one which is the ideal gas. So if I don't have any interaction, then Mayer already told us the F terms will be 0. In the that's why he removed it. So then if I do, then only keep this term, then I the ideal gas. So the partition function is just the ideal gas term. Next term then is this binary interaction term, 2 particle term, and this becomes your second virial coefficient in certain ways, you will see that. And this is the 3 particle term has of 2 kinds. One we call chain diagram, because this is 1, 2, so this is this kind of term F12, okay, this F12 F23, the one I have done here is this thing, this is F12 F23, right. So all the combinations of 3 particles but chain diagrams, they are not, but this one is everything is doubly connected. So this one if I draw the graph, I will find 1, 2, 3, because 1, 2, 2, 3, 1, 3 or 3, 1. This is a different beast. These are called ring diagrams in the language of physics and chemistry. Yeah. Now, these are the chain. So let us see what did Mayer do with all this beautiful stuff. So this is called decomposition of a partition function. This is the universal. This is the one which is used in everywhere in your physics and chemistry, in many body. When you talk of many body physics, this is what is done. If you take Fetter-Wallach or any many body physics books, this is the first thing that anybody do. And there it is called Mayer cell cluster expansion. Okay. So now there is a graph theoretical representation. The first term is unity ideal gas term 1 dot no line and ideal gas. Second term two dots and a line, and the black dots also has a meaning, and I will come to that. Black and white is meant, that is the graph theoretical language that is used, and there are such figures or graphs. Then third term is these 3 dots, 2 lines and 3 lines. So one is a chain diagram which has 2 lines and 3 lines. So then the line is a bond. Line can be considered a bond because there is an interaction between them, and the bond is a kind of mathematical bond because the F is has the characteristics. You have to remove the hard-sphere part to make it into a chemical bond. If you do that, it is called a physical cluster, which has also been developed, but we are not going to go into that. Now, as I was saying, the dots means in statistical mechanics and there that it has been to be integrated over. However, if I have an external field, which I can add an external potential like in a homogeneous system, like you want to take of an external electric field which is position dependent, or you want to take of surface effect as a wall which has an interaction potential at certain specific location, then that has to be included in your description. Then you need to have an extra term plus UR to be there, and those particles which are facing that will be, you cannot integrate them anymore. So then those will become, we call them white circle. These are the things done. So this more sophisticated version of that, there is a beautiful review article by George Stale 1963, and then one little before that Morita, T. Morita 1961, but the George Stale essentially did the work of Morita, and this is in a book Physics of Simple Fluids, edited by H.L. Frisch and Leibowitz, and there in half of the book is George Stale's article and graph theoretical representation. Okay. Now what I have to do now? In order to evaluate the partition function, I have to sum over all these diagrams, right? All these diagrams need to be summed over. How do I do that? It is a formidable. So we have made some progress. We have now beginning to see that how I am getting ideal gas law. I am beginning to a decomposition. Things are simpler, but I have not solved the problem. All the difficulties are now hidden in these terms. I have a graph theoretical representation of interaction between particles which is neat and clean, but I have to make further progress. Next thing what Mayer did was, he said okay, he realized that this is a dot is a kind of a 0 particle, these are 2 particles, these are 3 particles, then I can go on and have that. The next one, if I have, of course I have 4 particles in a many body system, then I will have diagrams which are connecting 4 particles. Now then what he said, okay, all these which are 3 particles, he bunch them together. Then there are 4, he bunched them together, knowing very well that there is a difference between them. One realizes that this one is essentially product of this one, okay, and I would be able to evaluate them if I know how to integrate this quantity. But that at this point not necessary, because I need to bunch them together according to number of particles in a cluster. So let me call them a cluster. This is where cluster expansion comes in. And I bunch these together knowing well there is a difference, but I call them together. So this is what now called the cluster integrals. So all the L particles are brought together, they might be they are all connected, they might be doubly connected, that is okay, it includes all of them, they can be even more than doubly connected, because if I have 4 particles, then not only it can be ring, it can be line in between. Okay. So I can have so 4 particle cluster consists of all versions of that, then this, then this, then this. Okay. It turns out that If we don't have any of them, then it is same as, it can be replaced in terms of the integral of f1 to ring one also can be done with certain difficulty, but this one becomes very, very difficult. You have to remember this particular thing is an integration on 4 particles. So, there are 4 particles into 3, each particle has 3 coordinates. So, this is a 12 dimensional integral. I can select origin as 1, but still I have 9 dimensional integral to take. And this was the difficulty that one could do, but some people were extremely brave. They did evaluate up to 5, 6. For Hart sphere one can do up to 9 or 10, and that gave rise to beautiful theories, Stana and Kahn and Starling and all these things, which we might not have time to go through. But there's amazing, exciting things happened in 60s and 70s, where because it had to wait little bit till that because of computers to come into existence, and these have played a extremely important role when it was put on the lattice in critical phenomena. That was called the high temperature expansion or series expansion done by Dom and Green and many other people. Okay. So, the reducible cluster integral of size L is this best. I put all the graphs together. Okay, I have put a normalization here. You will see that is very useful. I have put a V here, and this is this particular thing has a volume V to the power L. Okay. Now, when I do that, then for example B1, then I get 1. And I do B2, then it is this quantity dr1 d2. I put this is a definition right now, and it will be handy definition. So, I have put certain normalization here, knowing what will happen. So, this is a definition which will be absorbed, so nothing to worry about that. So, I now calculate B2. B2 now, this diagram. So, that diagram, as I look at a diagram, I immediately know I have to integrate over this, I have to integrate over that, and I have f12 there. And that is the advantage of a graph, or that's the whole thing of Feynman's graph theoretical technique, was that they could write down the graphs, and then from the graph, so you don't go do the algebra. Instead, you write down the graphs and then translate the graph into an integration. Okay. Similarly, we are doing, so this becomes that. So, now I see dr1 d2, why it has put in, you can now understand. I can change my coordinate to 1, so then it becomes 1 2, and this is 1 2. So, I can integrate over my origin, there is nothing, so long there is an external field. So, then that volume cancels this volume, and then I get and dr1 2, I call that back r. So, that is 4 pi r square, and dr 4 pi r square f1. And this is the B2. You are beginning to see certain things that radial distribution function kind of nature character is coming out. B3, which is a lot of fun. You have now this 3 dimensional integral, f1, f31, f21, f12, f3, all these things together. I do not know where f12 has disappeared here, but it has to have f12, f23, everything. I think my student whom I told to cut and paste, I think he did not take from the book. I think he is very, very, very ambitious guy. He decided that he will learn it again, and in the process everywhere he is making mistake. Okay. So, it has to have the, he has put it here, not the right way. So, f12 should come before, and then 2 1 3 1. So, it is correct, but not the way I would have written it. So, and this is the 3 particle term. I would have written at 1 2 2 3 3 like that, but that is the same thing here. Okay. Now comes a lot of fun. This is really beautiful term. Now we have to say that if I go back to partition function, then I have to make 2 things. How can I group them together into one term and then I can calculate how many of them are there. So, 2 steps, and this is a little difficult, but please try to think. So, some contribution of the configuration integral of all the clusters of size L, look at that sum over all the connected things. So, now this is the quantity I want. This is still very formal. I am grouping them together, I am not evaluating them. Please do not get it wrong. I am just grouping them together. I am developing a language, a semantics to be used. That is how a big problem is done. A big problem is divided into bits and pieces. Divide and conquer. I am dividing it now. The conquer part will come later. Okay. So, that division I have now introduced cluster integral. It is called Mayer's reducible cluster integral. And that now, so what I need in the partition function is this part. That part is then BL L factorial V, okay, and all the particles there that I know how to do. So, then the sum contribution to configuration integral, the thing that I have written here, all 3 particles are here, all 3 particles are here, that would be then all the L factorial to the power ML, because ML is the number of clusters of size L, and all of them come with the same weight VBL by definition. So, VBL to the ML. This you can just do work out, one of them you will find this is exactly includes everything. Now comes the important part, that, so this is the total contribution. So, if I have ML number and I will have constraint on ML, if I have ML number of cluster of size L, it is then I am now is going to do a combinatorics. I am going to say how many ways I can distribute or I can put essentially marbles into boxes, and the boxes are my cluster of size L. So, I have n number of particles, I have to put them in boxes. So, it is a very famous combinatorics, I think in one of the very popular problem in IIT JEE in called multinomial distributions. Actually a very typical, those who have done IIT JEE, this is one popular, they every 2-3 years this comes, even then is very difficult to do. So, basic idea is that I have a constraint. What is the constraint? Constraint is that total number is L to Mn. So, then total number of molecules in ml cluster of size L. So, total number of molecules n, and in LML is the number of particles in cluster of size L. Like if M20, L is 20, then there are 20 particles. So, in order to get the normalization, I have to do 20 into number L. So, it is so again you have the boxes. If the box is named 20, you put 20 balls there, okay, and then you find out how many ways I can distribute that. That quantity is this quantity, multinomial, okay. Alright, you have to do little bit yourself, but it is not difficult. Just do with a 3 particle, you will be able to do. If you like, there is a lot of, this particular part is a lot of fun. Then I want to get the partition function. So, this is the weight of total weight come to the partition function, contribution to the partition function, all L number of clusters. Those all L, like here all 3, all 2, and they, how many of them will be given by this, the total configuration of my system. So, what I have done now, let us see that I have instant configuration, and instant configuration I have M1 equal to 20, M2 15 and M3 equal to 5. Then it will change because my cluster distribution will change. I have to include all the cluster distributions, but each distribution, this 20, 15 or say 5, they will come with a weight. That weight is given here. The total number of ways I can get that, and this is the weight to the partition. So, that particular cluster size distribution contributes this much in terms of integrals to the partition function, and these match the number of ways I can form that cluster size distribution. So, I have to now multiply these two, and when I multiply these two, then this is L factorial get cancelled, and I get this beautiful expression called Meyer's, this is called Meyer's partition function, Zn by n factorial E BBL ML by ML factorial. So, let me write this down. Right, even now we have just on the way to do the things, we have not solved the problem, but we are on our way to solve it. So, Meyer partition function is the configurational part this is exact. Why it is exact? Because this is nothing but bunch of definitions. Okay. But now from there one can start playing some very interesting games. So, ignore that last part here with not important at this point. That means I am saying this part is not important at this point. So, this is the one that we need to evaluate. So, once we know Zn, remember if I know Zn, then I know the canonical partition function, and canonical partition function Qn is this 1 over h to the power 3n 2 pi m kbt to the power 3n by 2 into this is the canonical full canonical partition function, and free energy equal to minus kbt ln q n. So, this is the equation number 1, this is could be equation number 2, and this is the equation number 3, and this is called, this one that you are saying is a first expression of the cluster expansion and or the cluster decomposition, and then one goes on doing the so I will stop here because it is fairly formidable and there is no point of going, but I will really, if you want I can forward to Rajurshi the slides, but take a look into this, it needs certain familiarization. It is done in a better in more detail in my book, more explanations and everything is there, but this is, as I said right at this point, this is an exact expression. These cluster integrals are temperature and volume dependent. So, in this decomposition of the partition function into smaller or simpler terms, BL is very strongly dependent on temperature, because BL is the integration over Boltzmann factor. It is also dependent on volume, because you know your total range of you're integrating of the total volume. So, when B clusters appear, they fill the surface or they fill the volume, and this can be done many different ways. One way Mayer did is we will do other ways through exact recursion relations, that one can solve this problem again bit by pieces. So, next a part of the puzzle is to get the cluster integrals. So, in cluster integrals we know B1 equal to 1. Now, I want to do B2, and we So, I can calculate B2 now, and B2 is the FR, and beta is 1 over KBT. So, see, that is what I see. Even in the two particle there we have to have a quadrature, but I can trivially put, and for Hart sphere I can evaluate it exactly. This one that becomes your second virial coefficient exactly. That is one of the great achievement. Then when you go to B3, B3 has all these 3 particles. So, this is a 2 particle cluster. That means this B2 is this quantity. Now, B3 will be this bunch of this plus. Now, if you choose to neglect these ring diagrams, your problem is solved. All you need is F 1, 2, and that already shows gas liquid transition, the condensation, appearance of infinite cluster. So, the way theory always works, you have to work very hard up to certain amount of time. Then there are certain, you are beginning to get your rewards, and you begin to see how things happens, how interactions make things different from ideal gas, how interactions, even 2 particle interactions, formation of trees, because F1, 2 like that kind of open diagrams are the trees, how the trees come and they influence the thermodynamic properties of the system. Yes. What I am saying, what you can do, this is for 1, 2, 2, 3, that decomposes. When you do the integration, you connect, you choose here, then it will be this integral and this integral. No, the product of the two. Up to all the chain diagrams that you can do, just trivial. One is like a convolution, is one, it's no problem. And that is why ring diagram suddenly becomes so much more, even at that level, it becomes so much more complicated. Up to chain diagram, things are easy. And this is a very common thing in all over many body physics. Ring diagrams we can still do. There are certain ways to make certain progress. It is when you have lines inside the ring. So, this one now had become 9-dimensional integral. I can reduce it to 6 dimension, but I have to do it numerically then. But we can still make a lot of progress that we will continue to do. But I will change you, give you the slides, and you please familiarize yourself little bit, because what we will do from now, we will show some very important class of relations. Cluster expansion just does not mean this, it also means expansion of density in terms of fugacity, which is a very important part of physical chemistry. You can have an expansion of density in terms of rho equals sum over L BLZ to the power L. That is exact. That you can also do from grand canonical partition function. And that expression of the pressure in terms of BL, ZL is the fugacity. And elimination of these two cluster expansion gives you virial series. So now, for the first time, you really begin to see, and first time you see that why virial coefficients are used to extract the force field. Remember, the first force field in this world was extracted from virial coefficient. That was Lennard-Jones did it. First force field, the basic ingredient is the molecular size. Then is the depth, epsilon. So, remember Van der Waals made a mistake, he got a size 8 times in the molecular size, okay. But what Van der Waals did was actually building a kind of things attraction by hand, and a kind of a priori which did not work out well. So, Mayer for the first time gave expression, exact expression of virial coefficient, and we study the temperature dependence virial coefficient, which is very easy from the equation of state experimentally. Fitted to that gave you the Lennard-Jones potential, 1940s. That was the beginning of our force field culture. Okay. Even now, these essentially one of the part of the things that one uses. Okay, anything else? We'll stop here now.